Good day all, and welcome once again to my YouTube channel. Today we are going to be looking at chemistry, an interesting part of chemistry, which is kinetic theory of gases. I'll go straight to the point. Now, the reason for this kinetic theory of gases was because scientists could handle solids and liquids easily more than gases. So there was need for them to study the nature of gases, how they behave, especially when they are in motion. Because of course, you are aware that when you hear of kinetics, it talks about motion. All right. So there was need to study the behavior of gases in motion, and that was the need for them to postulate this kinetic theory of gases. So there are about five postulates, and I will run through the five, and then I will explain in details. So you just pay attention as I run through the series. For the number one of the postulates, first postulate is gas molecules in container move randomly usually in a straight line, colliding with one another and with the walls of the container. I will take that again. Gas molecules in containers move randomly in a straight line, colliding with one another and with the walls of the container. What does that mean? It means that when you have, let's say, a container like this, and this container is sealed, then you're not having gas molecules dispersed or evenly distributed in the container. What is usually observed is that the gases tend to move in straight line, colliding with one another and with the walls of the container. Because one thing is this, gases are known to move in random pattern or in haphazard pattern. So they tend to collide more frequently when they move in that random pattern. All right. So that is the first postulate of the kinetic theory. Then the second, the collision of between gaseous particles or gaseous molecules is perfectly elastic. I'll take that again. The collision of gas molecules is perfectly elastic. And what does that mean? It means that when gas molecules collide or they meet with each other, what happens is that there is usually no loss of energy. And what does that mean? Let me give you an illustration. Let's say you have gas A and gas B, and the energy possessed by gas A, let's say, is 5 joules, while the energy possessed by gas B is, let's say, 7 joules. When gas A collides with gas B in a container, now it could be that gas A would now, after collision, move faster than gas B or vice versa. But then again, there is usually no loss of energy in the container. How? Let's say A collides with B. Let's say this is gas A colliding with gas B. Now, when they collide, remember that A had 5 joule before collision and B had 7 joule of energy before collision. So colliding then now led to A having more energy, let's say 9 joules after collision, and B is now having, let's say, 3 joules. So in this case, observe, before collision, when we sum up the energy that they were initially possessing, we will have 12 joules. That's before collision. Then now, after collision, they are now having 9 joules plus 3 joules. That gives still the same 12 joules. So that confirms the fact that gases are, whenever they collide, they are usually in a perfectly elastic manner. All right. So their collision is usually perfectly elastic. Then three, the postulate three, the actual volume of gas molecules is negligible compared to the volume of the container. The actual volume of gas molecules is negligible compared to the volume of the container. And what does that mean? It means that the actual volume of gas molecules is almost insignificant when compared to the volume of the container. So it means, let's say we are having this container And in this container, the liters of this is actually 2 liters. And let's say we are now having, 50 liters here. This is 50 liters. Now you can actually transfer gas from 2 liters to these 50 liters, and it will fill up every part of the 50 liters, indicating that gas molecules tend to what? To spread easily. All right, and then it fills up every part. So it means that it's not, you cannot get an actual volume of the gas, you can only get the volume of the container. You get the point? So that's the reason why we say the actual volume of gas molecules, they are negligible or almost very small and insignificant. So that's the reason why that postulate was actually brought up. Then number four, the cohesive forces between gas molecules is negligible too. And what does that mean? It means that I've even explained it based on this. Meaning the moment you transfer gas from a 2 liter container to 50 liter, they spread evenly and they would not be held together by any force because it's almost insignificant. There is no force holding or connecting the molecules, the gaseous molecules together. So that's the reason why that postulate is somewhat linked to the previous one, meaning the fourth one is somewhat linked to the third postulate. Then the fifth postulate, the temperature of gases is a measure of the average kinetic energy of the gaseous molecules. And what does that mean? It means that temperature has a link with that of the kinetic energy possessed by gas molecules. Of course, an increase in temperature tends to increase the rate of movement of gaseous molecules. Yes, so it means the hotter the gaseous molecules, the faster their rate of movement. And the cooler the gaseous molecules, the slower their rate of movement. So that's one thing that is so clear. Now, looking at these five postulates, so many students will be wondering, why do we even study it when ideal gases or perfect gases, to our own understanding, they do not exist. They are only imaginary gases. But then again, sometimes we have to understand these things because it will be of utmost relevance, especially calculations involving gases, talking about the gas laws. Now, the gas laws obey the principle of the kinetic theory of gases. So that's the need for we to understand the kinetic theory of gases. All right. So in our next video, we'll be looking at the gas laws. And considering the gas laws, we have quite a number of gas laws that we need to understand. Talking about Boyle's law, Charles' law, Avogadro's law, Deluxa's law of combining volumes, and then Dalton's law of partial pressure. We have Graham's law of diffusion and the rest. So we are going to cover this series. So this is just the first part of the video. Then thanks for watching and stay tuned as I run through the series together. So in the next video, we'll be looking at the introduction to gas.